Hey guys, in this video we're going to be talking about describing motion under constant acceleration with kinematic equations, describing the motion of objects in freefall, and analyzing motion using graphs. So first let's talk about what constant acceleration means. So this means that in the context of a problem or situation in constant acceleration, the acceleration of the object does not change. Whether it's 0 or 5 meters per second squared or negative 3 meters per second squared. It's not going to change. So let's quickly remind ourselves about what acceleration is. So if our acceleration is 0, say 0 meters per second squared, then the velocity is constant. So this is like a car cruising at 35 miles per hour without slowing down or without getting faster. If we have positive acceleration, let's say positive 3 meters per second squared, then an object is either speeding up in the positive direction or slowing down in the negative direction. And in 1 or 2 dimensions, we take right or up to be the positive direction and left or down to be the negative. Negative acceleration, let's say negative 5 meters per second squared, means that the object is either slowing down in the positive direction or speeding up in the negative direction. Okay, now that we've talked about what constant acceleration is, let's talk about how to describe motion in constant acceleration. So the first equation that we're going to derive is the equation final velocity is equal to initial velocity plus acceleration times time. Now the way we're going to derive this is we're going to remind ourselves that acceleration is equal to the derivative of velocity with respect to time. However, if acceleration is constant, then instantaneous velocity is going to equal average velocity. Think about that for a second. When acceleration is constant, whether it's 0 meters per second squared or any other value, as long as it doesn't change, instantaneous velocity is going to equal average velocity. Okay, so that means we can just set A equal to V minus V0, final velocity minus initial velocity, over the time interval. And throughout these kinematic equations, we're just going to let initial time equal to 0. So that means we're just going to have t in the denominator instead of t minus initial time. Okay, now we can rearrange the equation by multiplying t to both sides. And finally, we are going to add initial velocity to both sides. So we end up with this equation. This is our first kinematic equation, and kinematics just deals with the description of how objects move. So this is our first kinematic equation. The next one is going to be average velocity is equal to the average of initial and final velocity. In other words, initial velocity plus final velocity over 2. Now the reason why this is true is that the velocity changes at a uniform rate throughout constant acceleration. So the average velocity is going to be halfway between the initial and final velocities. This is our second kinematic equation. Now next up, we're going to be deriving final position is equal to initial position plus initial velocity times time plus 1/2 times acceleration times time squared. Now, first we're going to use the definition of average velocity, which is that average velocity is equal to final position minus initial position over elapsed time, which is t in this case, because we are going to set initial time to 0. Rearranging the equation, we have x minus x0 is equal to average velocity times time. And then we're going to add initial position to both sides. So we get initial position, or final position, is equal to initial position plus average velocity times time. Now remember our second kinematic equation wrote average velocity as the average of initial and final velocity. We're going to use that substitution here, and we're going to get that final position is equal to initial position plus, in parentheses, the average of initial and final velocities times time. And then we're going to manipulate further by distributing time to the numerator here. And then we're going to substitute our first kinematic equation, which was velocity is equal to initial velocity plus acceleration times time. And if we do that substitution, we're going to get final position is equal to initial position plus initial velocity times time plus initial velocity plus acceleration times time over 2. And here we substituted with v equals initial velocity plus acceleration times time. And then simplifying, we're going to get this. Which, as you can see, was the kinematic equation that we set out to derive. So there it is. This is our third kinematic equation. Now for our fourth and last kinematic equation, final velocity squared is equal to initial velocity squared plus 2 times acceleration times the displacement, or final position minus initial position. I also like to just remember this as velocity squared equals initial velocity squared plus 2AD for displacement. This makes it easier to remember for me personally. Now, the way we're going to derive this is we are going to use the equation over here. We're going to use x equals initial position plus average velocity times time, which again we derived from the definition of average velocity. So we're going to write that out here. We're going to use final position equals initial position plus average velocity times time. And then we are going to substitute average velocity with the average of initial and final velocity again, just like we did last time. And we're going to get this. And now we are going to solve for time. Then what happens is we are going to subtract initial position from both sides. Now at this point, we're going to be using the equation v equals v0 plus at, and then isolate the variable t here, like this. And then here we're going to substitute this value for t into this equation. Then what we get is final position minus initial position is equal to average velocity times time, which is written like this. And then multiplying, we're going to get v squared minus initial velocity squared over 2a. And then that's how we get v squared minus initial velocity squared is equal to 2a times final position minus initial position, or 2 times acceleration times displacement. So this is our fourth and last kinematic equation. Okay, so to quickly sum up the kinematic equations we have so far, I'm going to write them down for you here. And remember, these only take place under constant or unchanging acceleration. So if your acceleration changes in any way, whether it changes in magnitude or it changes in direction, because acceleration is a vector, then these kinematic equations probably do not hold. In fact, they won't hold because it's not constant acceleration in that case.